Good morning. In this lecture video, I'm going to explain addition of multi-byte number. So in the previous video, we observed addition of 8-bit number and addition of 16-bit number in a direct approach. So if it is a multi-byte addition, direct approach is not efficient. So that is why we do another efficient method that I'm going to explain in this lecture video. Let's consider an example. Write an ALP in 8051 to add multi-byte numbers. So remember, multi-byte means more than one byte. So 2 byte also can be considered as a multi-byte, 3 byte, or it could be 4 byte, anything. Multi-byte number stored in the internal memory. Internal. First number starting at the address 20H, and first multi-byte number stored starting from 20, and second multi-byte number stored starting from the address 60H. After the addition, store result in external data memory starting from the address 2000H. So this is the specification given. So to write the program, first we must understand the specification. That means a requirement. Here the program is to perform addition of two multi-byte numbers. First multi-byte number stored from the address 20H and second multi-byte number stored from the address 60H. And the result should be stored at the external memory address starting from 2000. Let's consider example of 4-byte number. We'll consider an example 4-byte number. So internal data memory for first number. So 1 byte, second byte, third byte, and fourth byte. So starting from the address 20H. If it is 5 byte, so in the next memory location 0 to 4, there will be a 5 byte. And similarly, so this is the memory view. It has a second multi-byte number starting from 60H. That is first, second, third, and fourth. And will as you know, if you add 4-byte number, we'll expect the result 5 byte. So those 5 bytes will be stored for starting from the address 2000 to 2002, first, second, third, fourth, and fifth byte. This is the memory view. So we must understand the memory view, then only we can easily write the program. So in the direct approach, we use addresses, direct addressing mode. But here we use indirect addressing mode. Indirect addressing. That means we use one pointer register to point a start address of number 1, that will use R0, and we'll use R1 to point start address of number 1, so number 2, second number, and then we'll use DPTR to point start address of the result. Start address of the result. Okay. So first we should do initialization. So what's that? Start with the 00, move R0 comma hash 20H. That means we configure R0 to point start address of number 1. And then say move R1 comma hash 60H. So 60H is copied to R1. That means we configure R1 to point to the start address of the location 60H. That is start address of number 2. And similarly move DPTR comma 2000. That means DPTR is pointing to the location 2000, that is start address of the result. So this initialization is over. Now get the first byte of first number using the instruction move a comma at R0, and it's supposed to be added to the first byte of second number. It is pointed by R1. So simply say add a comma at R and add a comma at R1. So a having first byte of first number and R1 is pointing to the first byte of second number. It performs addition of those two, and the result will be in A, and that's supposed to be stored to the location pointed by DPTR. So say move X at DPTR comma A. Okay. So first operation is over. What's the first operation? Add first byte of first number with the first byte of second number and store the result. So after that we should move to the second byte. So R0 should be point to the location 21. So increment R0. So and then R1 should point to 61. Increment R1. And this pointers DPTR should be point to the 2001. So increment DPTR. So now after executing these three instructions, now pointers are pointing to second byte of first one, so first number. R1 points second byte of second number, and DPTR points next location of a result. Now we do operation of second byte. That means get the second byte using an instruction move a comma at R0, add with C. For the second operation, we use add with C. Add C A comma at R1, store the result. Again, for the third operation, increment the pointers. Third operation, increment the pointers. So after this, pointers are pointing to the third byte of first number, third byte of second number, and the location where third byte is supposed to be stored. Now, same set of instruction. Get the third byte, the first number into A, add with third byte of the second number which is pointed by R1, store the location, the result to the location pointed by DPTR. Okay, third byte of operation is over. Next, fourth byte. After this, points are incremented and pointing to the fourth byte. And the same set of instructions. Correct? So here it is not required to increment the pointer, but still will increment. It's of not a problem. Okay. So it is pointing to the last location, and here it is pointing to. Here we are supposed to store the carry. If there is a carry from the most significant addition of most significant byte, then the result is 0 1. Otherwise 0 0. So jump on carry, store 0 1. If no carry, copy A with the 00H that you copy into the location pointed by DPTR using instruction move X at DPTR comma A. Go to S jump here and here store. If it is carry, it will come to store 01. It stores I byte result 01 into accumulator and store that into DPTR to the location pointed by DPTR and end of the program. Control loop and end of the program. Clear na? So this is the program. This is the program. And observe here, same set of instructions. Not you see in the direct approach which we observed in the previous video, there was a difference. I mean, different addresses we have used. But here, same set of instructions. Same, okay? Same set of instructions. Only one changes. In the first set, this is the initialization. In the first operation, add A instruction. So this also can be done with the add C instruction, but we should make carry 0 before doing this operation. That is why. So in the initialization part, we'll say add clear carry, and then we can say RC here also. So now see, same set of instructions 4 times repeated. Same set of instructions repeated 4 times. So we'll use these instructions in a loop. So, and here how many times these instructions are supposed to be repeated? 4 number of times. Then that is called as count value. So if you want to add 4 byte number, count value is 4. If you want to add 5 byte number, count value is 5. So we'll store count value in any register. Let's say R2. Move R2 comma #4. So remember, count value means number of operations. Okay. And then so only one set of set of instructions are used. At the end of this, decrement jump not 0 R2 comma back. I mean, repeat these set of instruction until count value becomes 0. Until count value becomes 0. So if count is 0, it will come out of the loop. If it is not 0, it will go to back. So back means first instruction. First instruction is supposed to be repeated. Clear na? So now this is the efficient way of writing the program. So this is the complete program. So this first initialization. R0 to point start address of R number 1, R1 to point start address of number 2, TR to point start address of result. For first operation clear carry, and this is the count value, and get the byte from first number, add with the second number, store the result, increment the pointer, and repeat this until count value becomes 0. After that, check carry from the most significant byte operation. If carry, go to store 1, stores the most significant byte of result, that is 01 to the pointer pointed by DPTR. Otherwise, it stores 0 and it comes to here. This is the program. So this is an efficient way of writing the program for multi-byte operations. Now we'll see in the previous we consider the numbers are stored in internal memory. Suppose if the numbers are stored in external memory, see, write an ALP in 8051 to add two multi-byte numbers stored in the external memory. First number starting from 5020H and second number starting from 5060H. After the addition, store the result in internal memory. So that means this is the memory view for number 1, and this is for number 2, and this is for a result. And observe, if you use indirect addressing mode as we use in the previous case, so we need two DPTR to point number 1 and number 2, but we have only one DPTR. Okay, for external the internal memory, no, only one pointer is required, so we have two pointers R0 and R1. So then how we can do this? Observe here, see, I byte addresses are same for the number 1 as well as number 2. I byte addresses are same. So DPTR can be used as a two 8-bit register, DPH and DPL. So DPH value is same. DPH value is same. So, and low byte addresses are different. I mean here 20223, here 60263. Store this low byte address in one general purpose register, that is 20H. So sorry, see R2 is equal to 20H, that is start address, low byte address of number 1. And similarly we'll use R3, and there you store 60H, that is start low byte address of start address of a number 2. Okay. And then here we use R0 or R1. Now let's see the program. So first initialization. So initialization, DPH should be 50H. So move DPH comma 50H. That is I byte address of the numbers, both the numbers, number 1 and number 2. And R2 with low byte address of number 1, that is 20H. And copy 60H to R3, that is low byte address of number 2. And then R0 with the 20H, that is address of result. This is the initialization. And first initially we should make clear the carry, and count value, let's use R4, that is 4. Since we need to perform our addition of 4 bytes, so count value is 4. Okay. Now we'll see the operation. So to get the first byte of a first number, DPL should have 20H. So that is stored in R2. So say move DPL comma R2. That means DPH is already having 50H. Now the R2 is 20H. If we copy that into DPH, so together DPTR becomes 5020. That means it is pointing to this location. Get that number using an instruction move x a comma at DPTR, and store that in a temporary register R5. So R5 is having low byte, I mean first byte of a number 1. And then configure DPTR to point start address of number 2. That means low byte address is stored in R3. So move DPL comma R3. So DPTR becomes already DPH is 50H. So 50 and R3 is 60. So it becomes 5060. So it is pointing to the location 5060. Get that number into accumulator. So now accumulator having first byte of second number, and R5 is first byte of first number. So say add with carry a comma R5, add with byte of a number 1, and store the result into R0. Store the result into R0. Clear now? And then what we supposed to do? We need to increment the low byte addresses of number 1 and number 2. They are at R2 and R3. And as well we need to increment R0. So increment R2, increment R3, increment R0. Okay, and then decrement jump not 0 back. I mean first instruction back comes to here. So in the second iteration, once the pointers are incremented, R2 is 21. So it becomes 21. Get the number, store in R5, and then with this instruction it becomes 61. So DPT is pointing to this location, get the number, add with, okay, second number, and then store the result. So it repeats, okay, clear na? So this is how we can do. So even though we doesn't have a 2 DPTR, we observe the addresses, their I byte addresses are same, so that we copied into DPH, and low byte addresses are different, so that we stored in a general purpose register and we incremented that register. Okay. So this is the complete program. Okay. This is the initialization part. and then operation. This is the increment the pointers, and this is the uh, count value. Okay, and at the end we check the carry. This is what the program multi-bit addition. Thank you. We will continue the next video.